All right, so we're going to continue on. So last time I was mentioning that, these integrals that we're getting when we're calculating arc length, they aren't, the easiest things to evaluate. So we're going to do an example where we just set up the integral and not evaluate it, because that's going to be, typically if you run into this problem where you're trying to find the arc length of something, you'll set up an integral and then feed it into a computer. That'll do it numerically because you can't do it exactly. So we're going to set up the integral that gives the arc length of the hyperbola xy is equal to 1 from the point, let's see, so we're going to go from 1, 1 to 2, 1/2. And for this problem, you can use, whatever variable you want. You can use x if you want. You can use y if you want. If you look at the different x values in here, though, we go from 1 to 2 in x and 1 to 1/2 in y. So I think it's going to be easier to do the x, use x as our integration variable. So we're going to solve for y in this case. We're going to get y is equal to 1 over x. Because we need the derivative, I'm going to go ahead and calculate it. We're going to get minus 1 over x squared. And so what we're going to do now is we're going to write, so we're just going to do this problem. So the length then is going to be the integral. My bounds, I've already pointed out, are 1 to 2, square root of 1 plus dy dx squared dx. This is going to be the integral from 1 to 2, square root of 1 plus, and then I square negative 1 over x squared. I'm going to get 1 over x to the 4th dx. This is one of those integrals that we're not going to find an exact or an antiderivative for in terms of the functions we have. So again, if you'd run into this in real life, what you would do now is you would plug it into a computer, have the computer do it numerically. The book has an example where you go through and do you use an approximation method, which we didn't talk about, so I'm not going to do that. So then now we're going to talk about the arc length function. And so what this this answers the question. So if I wanted to find the arc length from 1 to 2 of a function, I would do the integral from 1 to 2, get a number. But if I had to go back and find the arc length from 1 to 3, I would have to do that integral all over again. So the question is, can I write down a function that gives the arc length starting from some point p0 to any point I wish. So what this is asking is, can I do the integral once and get a function that'll give me the arc length, to anywhere that I want? And the answer is yes. You might not always be able to do the integral, but you can always write it down. So we're going to call this arc length function. They call this one s of x. For me, s is always just arc length. But so the distinction here is this s is going to be a function. What we're going to do now is we're going to have our starting point here. Well, we're going to leave our final point to be a variable. And then we just have 1 plus dy dx squared dx. Or, you could do this in terms of y, the integral from a to y. Actually, sorry, yeah, so want to be careful there. Yeah, so let's do this. We're going to write this dy dx prime. So the reason I'm doing that is because you don't want this variable to be the same as that variable, because it's confusing notation. So we're going to use, dx prime. You can also use, maybe a little bit better once you don't have to drag around the primes, you can use dt. Because we're integrating, it doesn't matter what variable we use. And you can have something similar for, the y, if you're using y as your integration variable, and this would be 1 plus dx dt squared dt. Okay, so let's now take an aside, and we will give a geometric interpretation of this. So if you look at, you have s of x is equal to the integral from a to x square root of 1 plus dy dx squared dx. If I take the derivative of that with respect to x, if I use the fundamental theorem of calculus, I'm just going to get the whatever's in the integrand, 1 plus dy dx squared there. And so I can also, from this, because I have ds dx, I can figure out what the differential of s is. ds is then going to be the square root of 1 plus dy dx squared dx. And you can imagine squaring both sides. And from that you can get the equation ds squared is equal to dx squared plus dy squared. If I'm, being cavalier in how I'm treating these differentials. And this is, the most common form of, the idea of this behind arc length. So, if you think about this geometrically, you have to think about what differentials mean. So differentials have something to do with the tangent line here. So ds is interpreted as being this line here, the length of this line here. And then, dx and dy would be this. And so you have the Pythagorean theorem giving you this formula that I just wrote down. And the idea is, this formula, the ds squared is equal to dx squared plus dy squared, is really easy to remember. And if you treat these as things that can be used as like fractions, you'll be able to easily derive the arc length formula if you forget it. And even better, this works in however many dimensions you want. So if you wanted to be working in 11 dimensions, like I guess some theoretical physicists do, this would be, you could start with this and write down, you would have 11 variables, but you could find arc length in 11 dimensions if you wanted. So that's just kind of an aside with a geometric interpretation of this thing. It's not going to be, it's supposed to help your understanding of this, but let's just move on to an example. So this is our last example for this section. We're going to find the arc length function. So that s of x of the curve y is equal to x squared minus 1/8 ln of x with starting point p0 and the point is 1, 1. Okay, so from this, we're just going to we're going to apply this formula. S of x is equal to the integral from a, and in this case, a is equal to 1. So we're going to go from 1 to x, square root of 1 plus dy dx squared dx. So I'm going to stick primes on the x's there. Again, just because we need to be careful with our integration variable. Actually, let's use t's. I know I'm gonna drop those primes. It's gonna get confusing. Okay, so we're gonna treat, instead of y as a function of x, we're gonna treat y as a function of t. So let's figure out, so we have y is equal to x squared minus 1/8 ln of x. So we're going to need that derivative. dy dx is equal to 2x minus 1 over 8x. And let's go ahead and, so just to make things simpler on us, let's go ahead and figure out, what 1 plus dy dx squared is. So we have dy dx squared is 2x minus 1 over 8x squared. So if I square this, I'm going to get 4x squared minus 2 times the product of the two factors, so minus 1/2, plus 1 over 64x squared. So now I'm going to calculate 1 plus dy dx. I'm just trying to make this as easy as I can when I go to plug it in, so it's simplified as much as possible before I plug it into the formula. This is going to be 1 plus 4x squared minus 1/2 plus 1 over 64x squared. And so this is going to be equal to 1/2 plus 4x squared plus 1 over 64x squared. So now what you'll notice is this is actually a perfect square here. So this thing is actually just 2x plus 1 over 8x squared. And again, you can double check that. It is in fact true here. So we're gonna, this actually makes things a lot easier on us, because 1 plus dy dx squared is, something that's just squared. So when I take the square root of that, that's gonna make things really easy. So I then have that the square root of 1 plus dy dx squared is gonna be this, so we're gonna have the square root of 2x plus 1 over 8x squared. That's gonna be 2x plus 1 over 8x. So now my arc length function is going to be the integral from 1 to x. And now instead of using x's, I'm going to use t's and change my integration variable to dt. It doesn't matter here because, t is just a dummy variable. It's whatever its value is, doesn't matter because I'm going to integrate it out. And so we can do this integral now. So this is t squared minus plus 1/8 ln of t. I'm going to evaluate this from 1 to x. So when I do that, I'm going to get x squared plus 1 over 8 ln of x minus 1 squared plus 1/8 ln of 1. And so ln of 1 is 0. So this becomes x squared plus 1/8 ln of x minus 1. This is my arc length function. So what this means is, if I want to find the arc length from the point 1 to any point I want, I can now just plug in a value of x and figure out what that number is. And that makes things a lot easier on me. And you'll need to be able to do this in Calc 3. So what you'll end up doing with this is, sometimes it's easier to write things in terms of the variable s than it is to write it in terms of x. And so you'll need to be able to do this in order to write things as functions of arc length instead of functions of x. So I'm going to stop the video here. That is the last piece of this section. If you have questions, shoot me an email. You can leave comments if you see something that doesn't make sense. I don't think there are any mistakes in this video, but they slip by me all the time, so I'll stop